In the previous section, we looked at the relationship between Q, the reaction quotient, and K, the equilibrium constant. And if you'll recall that mathematically, Q and K are the same, right? You calculate them exactly the same. However, the difference was K was the concentration of things at equilibrium, and Q was the concentration of things at any given time point. And what we found was that if you had excess products, for example, the reaction would shift back to form more reactants. And if you had excess reactants, the reaction would shift to form more products. And basically, this is Le Chatelier's principle. Although there we calculated it mathematically, and here we're going to think about it more qualitatively, what we're looking at is essentially a fairly straightforward principle. The reaction wants to be in equilibrium. Okay, so this reaction wants to have however much of this and however much of this that it wants at equilibrium, such that the rate of the reaction going in this direction towards the products and the rate of the reaction going in this direction towards the reactants become equal. So if, for example, one adds more products, well, the reaction rate is going to go faster towards the reactants than towards the reactants forming products. Why is that? Because if we increase the concentration of something over here on the product side, the rate of the reaction shifts in order to go faster to get rid of that. Effectively, it shifts to make more reactants. If you add more reactant, it's going to do exactly the opposite. It's going to increase the rate of the forward reaction as compared to the reverse reaction. And the net effect of that is that you essentially shift to form more products. And this is Le Chatelier's principle. The reaction has an equilibrium, and it wants to be at that equilibrium. Before we look at some specific examples of how we can disturb the equilibrium, what I would like to talk about is, what is the utility of this? Why does anybody care? Well, there are many reversible reactions that are used in, say, the pharmaceutical industry, where they're trying to make either the end product or some intermediate product that is in some therapeutic drug given to people. Well, if those reactions are reversible and you want to get as much products as possible, right, because those products are useful, how are you going to do that? Well, usually what you would do is use one of the two reactants in excess. Why would you use one of the two reactants in excess? Because if you use one of the reactants in excess, there's going to be excess of reactant, which is going to drive the reaction towards products. Now, in some cases, there are ways to remove the products, so therefore that reverses the minimizes the reverse reaction and favors the products. And that's, works in some cases. The other thing to point out here is, well, which reactant are you going to use in excess, A or B? Well, usually it comes down to money. If A is cheaper than B, you're probably going to use A in excess. Unless there's some toxicity reason or it's really hard to get out of the reaction mixture or something like this, usually the cheaper one wins. So there is really strong utility to Le Chatelier's principle, and it's something that we discuss fairly regularly in the organic chemistry lab because many of those reactions are reversible. So now what we're going to do is look at this as a bunch of examples as opposed to me just talking about it in theory. So let's look at some examples. There are three things that we are essentially going to consider here. We're going to consider changes in amounts of products and reactants. We're going to consider changes of pressure, and we're going to consider changes of temperature. So these are, different stresses on the equilibrium, and we want to think about how each of these stresses is dealt with by an equilibrium reaction. So let's look at this case. In this case, we have 2x plus y yields x to y. And let's say this reaction is at equilibrium. Well, what happens if more x is added? If more x is added, the rate of the forward reaction increases, right? Because we've increased the amount of x, the concentration of x, so therefore the rate of the forward reaction increases. What is the net effect? The net effect is we get more product. Why? This reaction has a certain equilibrium. Note that doesn't mean x and y and x to y are equal. It just means the rates of the forward and the reverse reaction are equal. So by adding more x, the reaction says, hey, there's too much x here. The reaction only has one way to get rid of X. It's to turn it into X2Y. So the reaction shifts to the right towards the products to get rid of that excess X. It's a kind of a simpler way of thinking about it. So in this case, the reaction is going to shift. Ooh, my pen isn't working here. It's going to shift to the right, or you could say towards the products. Okay, so these are basically an arrow showing which way it shifts, the direction of the arrow, and towards products. What happens if Y is removed? So we have Y here, and we decrease its concentration in some way. Well, what's the reaction going to do? The reaction is going to say, hey, there isn't enough Y anymore. Some of it was removed. How can the reaction make more Y? Well, the only way the reaction can make more Y is to turn X2Y into X and Y. So the reaction in this case is going to shift to the left. And in this case, it's going to go towards the reactants. And again, these are just different ways of saying the same thing. Need a T there. What happens if X2Y is added? Well, the reaction says, hey, there's too much X2Y present. I need to get rid of it. How am I going to get rid of it? Well, the only way it has to get rid of it is to turn it into X and Y. So what is it going to do? Well, it's going to make more X and Y. And at the end of the day, it's going to shift left or towards the reactants to get rid of that molecule. Okay? So if we stress the equilibrium, the reaction responds to that stress by removing the thing that was added or making more of the thing that was removed. So this is what happens if you change the products or reactants in terms of Le Chatelier's principle. Simply put, Le Chatelier's principle is reactions will respond to stresses in equilibrium in an attempt to reestablish such equilibrium. Let's look at another case. Changes in pressure. So this isn't as straightforward as the previous case where we were simply adding more products and reactants or taking them away. What happens when the pressure is increased? Well, when the pressure is increased, we need to think about what's going on here that will affect pressure. Here we have gases, and as we know, gases exert pressure. But specifically on the reactant side, we have 2 X gases and 1 Y gas. We have 3 moles of gas. Okay? And on this side, we have X2Y, which is just 1 mole of gas. So when the pressure is increased, the reaction wants to decrease that pressure. How can a reaction decrease the pressure? Well, the reaction can do that by making less moles of gas. If there's 3 moles of gas on this side and 1 mole of gas on this side, if this shifts, there'll be less moles of gas in the equilibrium mixture, thereby decreasing the pressure or responding to the increase in pressure. So in this case, the reaction shifts to the right towards the products to decrease the pressure because 1 mole of gas will exert less pressure than 3 moles of gas. What happens when the pressure is decreased? Okay, so let's look at what happens when the pressure is decreased instead of increased. Not surprisingly, it's going to be the exact opposite. If the pressure is decreased, the reaction wants to shift to increase the pressure. How can the reaction shift to increase the pressure? Well, the reaction's only response here is to make more moles of gas. The only way it can do that is for X2Y to turn into X and Y. So the reaction wants to increase the pressure. So the reaction shifts left towards the reactants in order to increase the pressure of the reaction. Let's look at a final stress on the equilibrium. And this stress involves a change in temperature. It says the reaction below is an endothermic reaction, and it gives delta H. What happens when the temperature of this reaction is increased? So an endothermic reaction means that it requires heat energy to make this reaction happen. Okay, so heat is required to make this reaction happen. So we can think of heat for an endothermic reaction as a reactant because we require heat to make this go. So heat helps the reaction occur, or heat behaves like a reactant. So if we increase the temperature of the reaction and heat is a reactant, more heat is going to shift this reaction towards the products. In this case, right, or towards products. Okay, the same typo here. It says the reaction below is an exothermic reaction. Delta H is negative 1430 kilojoules. What happens when the temperature of this reaction is increased? Well, for an exothermic reaction, heat is given off when the reaction occurs. So in this case, we could think of heat as a product, right? Because this gets hot when this reaction occurs. So here, heat is a product. Well, what's going to happen to the reaction when the temperature is increased if heat is a product? Well, if heat is a product, adding heat is going to drive the reaction in the opposite direction. So in this case, the reaction shifts left or towards the reactants. So in all of these examples of Le Chatelier's principle, the reaction is shifting the equilibrium to minimize the stress placed on the equilibrium. Said another way, the reaction wants to maintain equilibrium, and the only thing the reaction can do is shift in one direction or the other in order to maintain such equilibrium. We looked at the effect of adding some reactants or taking them away. Or products as well. We also looked at the effect of pressure, and in that case, we had to consider the moles of gas on each side. And then finally, we looked at the effects of temperature, and in that case, we needed to consider whether we were having an endothermic reaction or an exothermic reaction. One last note is you won't be asked what will happen for a decrease in temperature. And the reason for that is that's hard to predict, right? Because temperature can decrease the rates of reactions in general. So there, it's not as straightforward as what will happen when the temperature is decreased isn't quite as straightforward here because there are other factors to consider as well.